Download this code from codegive.com, link in the description below. A comprehensive guide to merge total army, a programming tutorial with code examples. Merge total army, MTA, is a popular concept in competitive programming problems, especially those involving arrays or sequences. It essentially means combining two or more sequences into a single, sorted sequence. The term itself doesn't refer to a specific, standardized algorithm, but rather encompasses various merging strategies. This tutorial will explore different approaches to MTA, focusing on techniques like 1. Merging two sorted arrays. 2. Merging k-sorted arrays, or lists. 3. Applying merge sort, which inherently uses merging principles. 4. Optimization techniques. 5. Common problem scenarios. We'll provide code examples in Python, due to its readability, but the concepts are easily transferable to other languages like C++, Java, etc. 1. Merging two sorted arrays. This is the foundational building block for many MTA algorithms. The goal is to take two sorted arrays, ARR1 and ARR2, and produce a single sorted array containing all elements from both. Algorithm asterisk. The standard approach uses a two-pointer technique. 1. Initialize two pointers, I and j, to the beginning of ARR1 and ARR2 respectively. 2. Initialize an empty result array, merged underscore array. 3. While both I and j are within the bounds of their respective arrays. Compare ARR1I and ARR2j. Append the smaller element to merged underscore array. Increment the pointer of the array from which the element was taken. 4. After one of the arrays is exhausted, append any remaining elements from the other array to merged underscore array. Python code asterisk. Time complexity asterisk O, n plus m, where n is the length of ARR1 and m is the length of ARR2. This is because we iterate through each element in both arrays at most once. Space complexity asterisk O, n plus m, because we create a new array merged underscore array to store the merged result. 2. Merging k-sorted arrays, or lists. This is a more complex and common problem. You're given a list of k-sorted arrays and need to merge them into a single sorted array. There are several approaches. A. Repeatedly merging two arrays asterisk. This is the simplest approach to understand. You repeatedly merge two arrays at a time using the merge underscore two underscore sorted underscore arrays function we defined earlier. Algorithm asterisk. 1. Start with the first two arrays in the list. 2. Merge them using merge underscore two underscore sorted underscore arrays. 3. Replace the first two arrays in the list with the merged array. 4. Repeat steps 2 and 3 until only one array, the merged result, remains. Python code asterisk. Time complexity asterisk O, k sub 2 slash sub asterisk n, where k is the number of arrays and n is the average length of each array. This is because we perform merge underscore two underscore sorted underscore arrays, which is O, n, k 1 times, and the lengths of the arrays being merged increase with each iteration. Space complexity asterisk O, k asterisk n, in the worst case, due to the intermediate merged arrays. B. Using a min heap, priority queue. A more efficient approach uses a min heap data structure. A min heap allows us to efficiently find the smallest element across all k arrays. Algorithm asterisk. 1. Create a min heap. Each element in the heap will be a tuple, value, array underscore index, element underscore index. Value is the current element being considered from a given array, array underscore index is the index of the array the element comes from, and element underscore index is the index of that element within its array. 2. Initialize the heap by adding the first element from each array, if the array is not empty. 3. While the heap is not empty, extract the minimum element, the root of the min heap. This element is the smallest element across all arrays. Append the value to the result array. Get the array underscore index and element underscore index from the extracted tuple. If there are more elements in the array at array underscore index, add the next element from that array to the heap. Python code, using heap module. Time complexity *O, n log k, where n is the total number of elements across all arrays and k is the number of arrays. Each extraction from the heap takes O, log k, time, and we extract n elements in total. Space complexity *O, k, for the heap. C. Divide and conquer, merge sort approach. This approach mirrors the merge sort algorithm. You divide the list of arrays into smaller subproblems, recursively merge them, and then combine the results. Algorithm * 1. If there's only one array, return it. 2. Divide the list of arrays into two halves. 3. Recursively merge the two halves. 4. Merge the two resulting sorted arrays using merge_2_sorted_arrays. Python code *. Time complexity *O, n log k, where n is the total number of elements and k is the number of arrays. The recursion divides the problem into log k levels, and at each level, we perform a merge operation that takes O, n, time. Space complexity *O, n, due to the temporary arrays created during the merge process. Comparison of k-array merge approaches *. Approach time complexity space complexity advantages disadvantages. -- Repeatedly merging 2 O, k sub 2 slash sub *n, O, k *n, simple to understand and implement. Inefficient for large k. Min heap O, n log k, O, k, more efficient than repeated merging. Requires understanding of heap data structure. Divide and conquer, merge sort, O, n log k, O, n, generally efficient and well structured. Requires recursion, can have higher overhead. 3. Applying merge sort, using merging principles. Merge sort is a sorting algorithm based on the divide and conquer paradigm. It works by recursively dividing the input array into smaller subarrays until each subarray contains only one element, which is trivially sorted. Then, it repeatedly merges these sorted subarrays to produce new, larger sorted subarrays until the entire array is sorted. The merging step is, of course, a key component of MTA. Algorithm *. 1. Divide * if the array has more than one element. Find the middle point of the array. Divide the array into two halves, left and right. 2. Conquer * recursively sort the left and right halves using merge sort. 3. Combine * merge the sorted left and right halves into a single sorted array. Python code *. Time complexity *O, n log n, where n is the number of elements in the array. The division process takes O, log n, steps, and the merging process takes O, n, time at each step. Space complexity *O, n, due to the temporary arrays created during the merging process. 4. Optimization techniques. In-place merging, careful, while the standard merge_2_sorted_arrays creates a new array, it's possible to perform merging in place, especially if you know the exact sizes of the arrays and have enough free space in one of them. However, in-place merging is considerably more complex to implement correctly and often negates the simplicity and readability of the standard merging approach. It's generally not recommended for typical competitive programming scenarios unless space constraints are extremely tight and performance is absolutely critical. Implementation complexity is significant, and debugging can be challenging. If you need to do in-place merging, thoroughly understand the algorithm and test it rigorously. Early termination. If, during the merge process, you encounter a situation where all elements of one array are smaller than the smallest element of the other array, you can simply append the second array to the result without further comparisons. This optimization can provide a small performance boost in specific cases. Choosing the right data structure. For merging k-sorted arrays, the min-heap approach is generally the most efficient, especially when k is large. However, the overhead of using a heap might not be worth it for very small values of k. In such cases, repeatedly merging two arrays might be faster due to its simplicity. Pre-sorting. If the input arrays are not guaranteed to be sorted, make sure to sort them first before applying any merging algorithm. Sorting the arrays adds an n log n cost, where n is the number of elements to be sorted, but is crucial for the merging algorithms to function correctly. 5. Common problem scenarios. Merge total army concepts appear in various problem forms. Here are a few common examples. Merging sorted lists, or arrays. The fundamental problem of merging two or more sorted sequences into a single sorted sequence. Variations may involve different constraints on the size of the input or the expected output. K-way merge sort. Implementing merge sort where, instead of dividing the array into two halves, you divide it into k subarrays and then merge them. Interval merging. Given a set of intervals, example represented as start, end, pairs, merge overlapping intervals into non-overlapping intervals. This often requires sorting the intervals by their start times and then using a merging approach to combine overlapping ones. Merging sorted streams. Imagine you have multiple continuous streams of sorted data. You need to maintain a single, sorted stream of data that combines all the input streams. This is a real-world scenario in data processing and requires techniques similar to merging k-sorted arrays. Finding the kth smallest element in the union of sorted arrays. Efficiently find the kth smallest element in the combined sorted sequence of several sorted arrays. This often involves techniques related to merging and binary search. Example problem, interval merging. Problem statement. Given a list of intervals, where each interval is represented as a tuple, start, end, merge all overlapping intervals and return a list of non-overlapping intervals that cover all the intervals in the input. Example Input 1, 3, 2, 6, 8, 10, 15, 18. Output 1, 6, 8, 10, 15, 18. Python code Explanation One sorting the intervals are first sorted by their start times. This is crucial because it allows us to process intervals in order and easily check for overlaps with the current merged interval. 2. Iteration and merging We iterate through the sorted intervals, keeping track of the current interval. If the next interval overlaps with the current interval, we merge them by updating the end time of the current interval to the maximum of the two end times. If there's no overlap, we add the current interval to the merged intervals list and start a new current interval with the next interval. 3. Final result Finally, we append the last current interval to the merged intervals list and return the result. Key takeaways Understanding the basics mastering the merge two sorted arrays algorithm is fundamental. Asterisk choosing the right approach. Asterisk select the appropriate merging strategy, heap, divide and conquer, etc., based on the problem constraints, number of arrays, size of arrays, performance requirements. Asterisk optimization. Asterisk consider optimization techniques like early termination and potentially in-place merging, with caution. Asterisk adaptability. Asterisk be prepared to adapt the merging concepts to solve related problems, such as interval merging, k-way merge sort, and finding the kth smallest element. Asterisk data structure proficiency. Asterisk a good understanding of data structures like heaps, priority queues, is essential for efficient merging. Asterisk code clarity. Asterisk write clear, well-commented code to make it easier to understand, debug, and maintain. Prioritize correctness and readability over micro-optimizations unless performance is absolutely critical. By mastering these concepts and practicing with various problems, you'll be well equipped to tackle merge total army challenges in competitive programming and real-world applications. Good luck.